And then n equals 1 means we're going to start with n of 1. N can start at 0, n can start at 2, or even 17 in some cases. And then the number at the top of the sigma, in this case the 4, is the number at which we stop. So n goes from 1 to 4. N equals 1, n equals 2, n equals 3, and n equals 4. Notice, these are the counting numbers. We're not going to talk about any negative numbers and no fractional numbers for our indexing variable, in this case n. Sometimes we use I or j as an indexing variable. The 2n plus 1, you'll notice, is in parentheses, which means we're going to take the indexing variable, n, replace it with 1, and then 2, and then 3, and then 4, and get 4 numbers, and add them up. And at the bottom of the visual, you notice we've taken n equal 1. 2 times 1 plus 1 is 3, and there's your 3. We've replaced n with 2. 2 times 2 plus 1 is 5. And we replaced n with 3. 2 times 3 plus 1 is 7. And we replaced n with 4. 2 times 4 plus 1 is 9. 3 plus 5 plus 7 plus 9, the sum of those four terms is 24, which is the answer to our summation problem. And again, we will use the summation symbol in sequences and series, so I wanted to introduce it to you at this point in time. It's pretty simple. It just simply means an easy way of saying add these things up, okay? Now, let's take a look at the arithmetic sequence. What is an arithmetic sequence? And again, you should notice that when you use the word arithmetic as a noun, excuse me, it's a arithmetic. When it's used as an adjective, it's arithmetic. So let's look at our next visual, which is the arithmetic sequence. Notice it says arithmetic sequence, common difference. An arithmetic sequence, the difference between two succeeding terms is always the same. So, for example, the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., is an arithmetic sequence, since we add 1 to the previous number to get the next counting number. This is an arithmetic sequence, 1, 2, 3, 4, dot, dot, dot. In fact, that represents the counting numbers. The dot, dot, dot means and so on and so forth, forever and forever. The next sequence that's listed, highlighted on your visual, is -8, -3, 2, 7, 12, dot, dot, dot. What is the common difference there? Well, to find the common difference, you can either say, what do I have to add to one term to get the next term? Or let's take one term and subtract from it the previous term. Let's do it both ways. Let's take -8. What do I have to add to -8 to make it -3? Well, I believe that would be -5. No, it would be +5. Because obviously from -8 to -3, we're going up the number line. And therefore, we're adding a positive number. The way to check that is to say, hey, if I add 5 to -3, do I get 2? Yes, I do. And when I add 5 to 2, do I get 7? Indeed. And of course, 5 plus 7 gives us 12. What would the next term be? Well, since the common difference is 5, we're going to add 5 to 12 and get 17. Now, let's go back and investigate the same sequence, the -8, -3, 2, 7, 12 sequence, using subtraction. If I wanted to find the common difference by using subtraction, I could say -3 minus a -8. Subtracting a -8 is the same as adding a +8. -3 plus 8 is 5. So either way, we get the common difference of 5. The important thing is, once you get the common difference, check to see that indeed it is a common difference for all the terms indicated. Because it could be pretty sneaky if the first 3 or 4 terms look like an arithmetic sequence and then it changed. And I wouldn't do that to you, but someplace on a test you might see that. It's always important to investigate and verify that indeed this is an arithmetic sequence. And the last line in that visual, another arithmetic sequence, 9, 6, 3, 0, -3. Notice the terms are getting smaller, or lesser, we should say. And therefore it means that what we're adding is a negative number. You could say, well, we're subtracting. Either way, it's the same thing. And the common difference in that last sequence is -3. We add negative 3 to 9, we get 6. We add negative 3 to 6, we get 3, and so on and so forth. In fact, I ask you what would be the next term after negative 3 in this sequence. And you should say, well, negative 3 plus the common difference, negative 3, is negative 6. If you said that, you would be absolutely right. Now let's take a look at some symbology for use in arithmetic sequences. And that's our next visual. It shows us that we use A to indicate the term. And each term A has a little number subscripted, that is, below it. It's called a subscript, an indexing number. The first A is A1, the second A is A2, etc. So A1 is the first term. Very, very important, because as we saw in recursive functions, if we know the first term and we have a rule, we can get the second term. Same idea here. We're going to be very, very important to know the first term. Now, A sub n means the nth term. If n was 12, then A sub n would be the 12th term. If n was 100, A sub n would be the 100th term. And then D, lowercase d, is the common difference. What we add to A1 to get A2. What we add to A2 to get A3. And notice it shows you that on the last 3 lines in this visual. A2 is A1 plus D. Take the first term, add the common difference. A3 is A1 plus D, which gets us the second term, plus another D, which gets us to the third term. And A4 is A1 plus D plus D plus D. Looking at those 3 definitions, if you will, notice there's something common. Can you see a formula for finding A sub n? Because you'll notice that in every case, the number of common differences, the number of D's we added, is always 1 less than the little subscripted number under the A. That is, to find A3, we took A1 plus 2 D's. A4, we took A1 plus 3 D's. How about A13? If we wanted to find A13, we take A1 plus 12 D's. Okay, now I want to find A sub n. Let's go to the board and take a look. Well, we know that we start with A sub 1. And we know that we're going to add a number of D's, a number of the common difference. And rather than adding D plus D plus D plus D, we are going to multiply it by the number of D's. We saw that to get A sub 4, we added 3 D's. To get A sub 13, we added 12. 1 less than this number here. That is, what's in parentheses is 1 less than this, and that is very simple to write. That's n minus 1. And that is your formula in arithmetic sequences for finding the nth term. So in other words, practical use of this, let's assume that you had a salary structure where every 6 months hourly employees received the same increase. Let's say they received a dime an hour, 10 cents an hour increase every 6 months. Well, how much money would someone be making per hour after, let's say, 4 years? That would be 4 6-month periods. After 8 raises. Well, all we'd say is A1 is their starting salary, hourly rate. The difference is 10 cents. And n minus 1 would be the 7 raises they would have received after 8 periods. Okay, so 7 times the common difference. In other words, they'd be getting 70 cents an hour more than when they started. And there are many real-world situations that approximate this arithmetic sequence. Another word, by the way, for sequence is progression. Sometimes this is called an arithmetic progression. Let's look at an example of finding the nth term in an arithmetic sequence. The next visual shows us that. We are given the sequence 7, 11, 15, ... which means whatever is happening with 7, 11, and 15, that sequence continues. The question, is it arithmetic? Is there a common difference? Well, let's see. What do I have to add to 7 to make 11? 4. What do I add to 11 to make 15? Also 4. Yes, there's a common difference. You'll note it takes at least 3 terms to determine the nature of a sequence. We're asked to find the 21st term. Why? Because that's the question. In the real world situation, this could very well be something that happens in the 21st day or the 21st. The item in the sequence is important to us. The initial value, A1, is 7. Again, from the original information we were given. The common difference, D, is 4. We've already determined that. We write it in. And N is 21, the 21st term. Using our formula, A sub N equals 7 plus 20 times 4. The 7 is A sub 1, the 20 is 21 minus 1, N minus 1, and the 4 is the common difference. 20 times 4 is 80, plus 7 is 87. So the 21st term in this sequence is 87. Just like when we worked with recursive functions, we wanted some way to find out something without having to go through every single number as we went through the recursive function. Same thing here. We could have found the 21st term by continually adding 4. To 15, we get the 4th term, which is 19, plus 4 is 23. But this is much nicer. Imagine if you had to find the 1,000th term. Would you want to, write down all those 1,000 terms? Much easier to use this method, a simple formula to find the nth term in an arithmetic sequence. Okay, what is this thing called a series? And no, it really has nothing to do with the World Series. A series is a mathematical term for the sum of the terms in a sequence. Okay? Sometimes, for example, you could have a sequence, let's say in a business situation,